Now let's see if we can marry the idea of hypothesis tests and confidence intervals together into one kind of example. So in the US, the mean population height for 3-year-old boys is 38 inches and follows a normal distribution. Suppose a pediatrician believes that the genetics and environmental factors that exist near his practice mean that the average for 3-year-old boys in the local area is different than what it is for the rest of the US. He gathers a random sample of 3-year-old boys from his practice and creates a confidence interval with a computer. All right, so for whatever reason, this doctor believes that the 3-year-old boys in his area just are different than the rest of the US. So let's assume that it is the same as the US up until we can prove otherwise. So he believes that it's 38 inches unless we can prove it otherwise, right? And then he said different. He didn't actually pick a particular direction. So we won't either. We'll say not equal to. And that comes from the word different right there. Because he says different, that means it's a not equal to problem. All right, now how many 3-year-old boys were in the sample? Well, the degrees of freedom is equal to 14. And remember, degrees of freedom is n minus 1. So that means n is equal to 15. All right. Now, is it all right that the doctor's sample size is less than 30? Well, that's a good question to ask because for both the confidence intervals and the hypothesis test, we have the same assumptions. Let me go back to them right here at the top. So we need a simple random sample. We have that. We need n to be less than 5%. We surely have that. But is it okay that he only has a small sample size of, what was it? 15 little boys. So is that all right? And the answer is, yeah, it's all right. Because it says right here, it has to come from a normal distribution or be n greater than 30. The outliers kind of goes along hand in hand with the normal part. So it's okay that n is less than 30 as long as we know that it's normal. And we do. We know that this is normally distributed. So let me go type that up. There. It is all right that n equals 15 is less than 30 because we are given in the problem setup that the distribution of the heights of 3-year-olds is normal. 3-year-old boys is normal, excuse me. So it's okay if you have less than 30 as long as you know that it's normal. And it tells us that it's normal right here, that normal distribution part right there. So because it gives this to us there, then we have it down here, and therefore it's okay that n is small. Now, what was the average height of the 3-year-old boys in the doctor sampled? Well, that would be the sample mean, which is 37.2. Now remember from chapter 9, if I didn't give it to you right there, you could find it by taking the average of 35.54 and 38.86. But it was given in this example, so let me type that in. X bar is 37.2. There, we got it. All right, now, using the confidence interval, did the pediatrician find a statistically significant difference in the height of local 3-year-old boys? All right, so statistical significance would mean we're able to reject the null hypothesis. But we are not able to reject the null hypothesis, and I've drawn you a little picture here. So you have 35.54 over here, you have 38.86 here, and then you have your mu zero, sorry, that's a little mu zero in there, is equal to 38. Well, 38 is not different. He was claiming that it was different, but we don't have that because our value is right there in the middle of our interval. So no, the interval does not support the claim that the mean is different in his area because mu zero, which is our hypothesized null hypothesis value of 38 inches, 38 inches, is contained within the interval. Okay. If mu zero was, say, 40, that would be different, right? If mu zero, let me make a comment. So note, mu zero pressed the wrong button. Sorry about that. If mu0 equals 40, then the interval would have supported claim because 40 is outside the interval, right? But since he claimed it was different and 38 is still in the middle of our interval, so it's not different that we can support. It doesn't mean he's wrong. It just means we didn't have the evidence to prove it. And that's what we write for our conclusion. So we say there is not enough evidence to support the claim that the 3-year-old boys in that pediatrician's practice area are significantly different in height than those in the rest of the US. Remember, this doesn't mean he's wrong. It just means that we couldn't prove it. There, and I just added that. This doesn't mean that the pediatrician is wrong. It just means that, because to be wrong would mean we're 100% sure. It just means we didn't have enough evidence to support his claim. We can't be 100% sure he's wrong. We think he's wrong, but we're not 100% sure. There, I thought I'd add that bit and just kind of separate it a little bit so it's easier for you to read. So we think he's wrong, but we're not 100% sure. We're never 100% sure, actually. We're never 100% sure. In this case, we'd probably be around 95% sure or so, if that was our alpha. Although I never actually told you what alpha was. Oh, but I do tell you alpha. Alpha is 5% because your confidence level is 95%. I should probably add that right in here. Also note, because our confidence level, C level, equals 95%, means that alpha, which is our level of significance, is 0.05. That'd be the probability of making a type 1 error there. All right, with that, we are all done with section 10.3. So I'll see you back here for 10.4 when we're going to do hypothesis tests yet again, but this time for variance and/or standard deviation. It'll be the same system for either one of them, more or less. See you then.